Hello, welcome to my ongoing discourses on Bergson's philosophy with emphasis on his holographic aspects. This is part two, and we'll be discussing James J. Gibson and his relationship to Bergson. We'll be discussing Gibson's notions of invariance laws and how that relates, and invariance as the modulated information for the brain as a reconstructive wave. A brief review of last time, part one. The universal field for Bergson is a holographic field. That is, it's a vast interference pattern, and as such, it's utterly non-imageable. This field looks nothing like the external world that we know. The brain is a modulated reconstructive wave passing through this holographic field. So the brain is not just a hologram, it is a modulated reconstructive wave passing through the field in Bergson's concept. This brain-supported wave is specific to a source in the holographic field. By this process, now an image. For example, the coffee cup on our kitchen table. So again, as in the little picture above, the reconstructive wave passes through the hologram plate, and there is specified to the viewer the recorded wavefront of the cup. It is a source of the wavefront. Now, there's no image of the coffee cup in the brain. Again, the brain is, or the wave, brain/wave is simply specific to or specifying a source in the holographic field. But there's no viewer, no homunculus inside the brain either, looking at the external image. We'll discuss how Bergson removes the viewer in part three. This is also the problem of the relationship of subject and object. We'll talk about Gibson's view of the nature of the image very shortly here, but first let me talk about James J. Gibson very quickly. 1904 and 1979, Gibson was a great theorist of perception in the discipline of psychology. A couple of his significant works or books, The Perception of the Visual World in 1950, The Senses Considered as Perceptual Systems in 1966, and others. My relationship to Gibson is through my thesis advisor, Bob Shaw, who was Gibson's student for some time at Cornell. And Shaw ultimately went on to found the Journal of Ecological Psychology, which is the premier journal for the followers of Gibson in the psychological field. If you want to see a little bit more of this relationship, you can see my little book, Time and Memory, a primer on the scientific mysticism of consciousness, for more of that story and Shaw's contribution to this whole set of thoughts. Now for Gibson too, there is no image being generated inside the brain. For Gibson, the brain, yes, like a wave, is resonating with information from the environment. Resonance is a concept that Gibson moved to because the information that he saw exists over time, and resonance is a time-extended phenomena. As we shall see, we have lots of invariants that are defined only over time, and we'll be looking at that. Therefore, the brain itself is specific to the environment, or specifying the environment. So it should sound a bit familiar. That is, Gibson already has resonances, shall we say, of the holographic wave reconstruction process. So let's look at this information that in the environment that Gibson had looked at, identified, and discussed. So firstly, we start with the problem with the perception of distance. And in the historical course of things, Bishop Berkeley, 1750, philosopher, had noted that if one takes a line in the picture above, we take the line ABCD, D obviously being further away than A, etc., but that the points all project to the same point on the retina. So if you move the retina or the eyeball there back and forth, nothing varies. There is no variance, and therefore there is no information, he argued, for depth. This led him to other theories on how do we perceive depth related to acting, etc. For Gibson, the ground became the operative concept, the ground line G1, G2. He noted that the points in the ground, W, X, Y, Z there, with their relative distances, are preserved relative distance-wise on the retina by a projective transformation. So there we have a projective transformation in the picture, and we note that on the retina, the back of the eyeball there, though inversed, we see the same relative distances. So the ground is upside down, shall we say, on the retina, but the same distances are preserved by this projective transformation. So there is indeed information from the ground specific to specifying distance. Now this got extended as to the structure of the ground. On the ground that we perceive everywhere, what's called, what he termed texture density gradients. In my little picture there, we have a gradient of increasingly smaller little elements, but these could stand for beach sands or blades of grass on a lawn or the gravel of a gravel road, any number of things, tiles on your kitchen floor, etc. But these have a precise mathematical relation, and this is where we're starting to talk about the information in the environment that's used to modulate the brain as a reconstructive wave. So the horizontal separation going across the screen there is a function of the distance to the observer. It's inversely related to the distance from the observer, or S is proportional to 1 over D, making an inverse relation to the observer. So in other words, the separation decreases as the distance increases. The vertical separation going up and down the screen here also has a relation, and that is it's inversely proportional to the distance squared. So the distance between the rows decreases as a function of the distance squared, or the distance as the distance grows by the square. These fields, these texture density gradients, are ubiquitous, and if you turn this upside down, you get a ceiling. If you put them sideways, we get the corridors. And so all told, they're again using their gradients, and they're very specific to the distance as it recedes from us. Now, these texture rows or gradients have another nice property. Here we have a cup. Now, when we move the cup back and forth, it stays constant to our perception. For example, I'll move my cup. Okay, so the problem here is on the retina, these cups are two different sizes. So why does the cup size seem to be the same when I move it back and forth? And the answer is there is an invariant relation between the size of the cup and the number of texture rows that the cup occludes. If you notice, in the back cup occludes roughly 4 rows. The front cup occludes roughly 2 rows. So what happens is, as the size of the cup or the height of the cup increases, the number of rows occluded decreases. And we can describe this little invariance law as S is proportional to 1 over n, or the size increases as the number of rows decreases. This is an invariance law. It's an invariant ratio, and it's an important piece of information for controlling action as well. Because if I'm trying to grasp the cup as it's moving toward me, this is a law specifying the size constancy of the cup that the hand-arm system would be using to grasp the cup. So I've already noted that here, I see. It is also information underlying virtual action, which is a concept we discussed in part 1, and we noted that action, the body's capability of action, is what makes relevant information in the holographic field. That is, it is the criterion by which information is selected from the vast amount of field in the holographic field, or the holofield. And we'll be exploring the notion of virtual action more as we go along. Now, if we put these texture density gradients in motion, we get what Gibson termed an optical flow field. An optical flow field is an array of velocity vectors. Imagine yourself moving toward these mountains, and flowing by you is the whole landscape, including the road. Now, each vector, the value of each vector, the speed of each vector, is inversely proportional to the distance squared, right? V is proportional to 1 over d squared, which is to say, the farther away the vector from the eye, the lower the velocity, or the closer to the eye, the higher the velocity. These fields, optical flow fields, are ubiquitous. For example, when we're driving down the road, like I noted, we have this very precisely mathematically specified flow field flowing by us. This flow field has a nice little ratio. I've just noted over to the right side there, we'll go into, that is called the tau ratio. And the value of tau is used to control the severity of, or specifies the severity of impending impact. So a bird coming in for a landing is using in his action systems the tau value to control how the softness of his landing. Or a pilot, for that matter, as he flies into the airfield to land, is using the value as his field flows toward him, the tau value, to control the softness of his landing on the airstrip. So tau is a very important invariance law related to action, acting, controlling impact. So all of these are examples of invariance or invariance laws. The velocity vectors and distance, the height of the cup and the texture rows occluded, the vertical separation of texture units, the tau ratio, specifying impact severity. In other words, this is the information specifying the environment, that is the external world. And as we think about the brain as a reconstructive way, we have to be realizing that this information is necessarily part of the processing and part of the very concrete wave that the brain is. And I'll say right now, and quite frankly, it's amazing how cognitive science simply ignores this, but moving on. This brings us to form. Form appearing to be normally a nicely static thing. But in truth, what we've moved to is the notion of flow fields again, Gibson's flow fields as fundamental for the specification of form in our world. So here we have a flag that's rotating. And as the flag rotates towards us, there's a flow field defined over it. It's a stiff flag. And that flow field would be expanding as it rotates towards us. As it rotates away from us, the flow field would contract. Well, so the lines of arrows would tend to contract toward a point, toward inward, toward the center more, etc. So if we generalize this a bit to what I like to call the Gibsonian cube, we see more implications. For example, here we have a cube that's rotating, and what we see on the one side, the right side, is an expanding flow field as the side turns towards us. The frontal face is a briefly parallel flow field, and as that face turns away from us, we'll have a contracting flow field. And on the top, we have a radial flow field. So we ask, what are the edges? What are the vertices in this Gibsonian cube, this cube of flows? Well, there's each edge, each vertice is simply a sharp discontinuity at the juncture of these flows. So these edges, vertices as features, are very dynamic things. They're creatures of flow. They don't exist without flow. Now, when you think of a cube just sitting there happily on my kitchen table at rest static, one asks perhaps how this applies, but the fact is your eyes are always in what's called saccadic motion. They dart to and fro over the cube in saccades. And we know that if the image with an apparatus of the cube is fixed on the eye such that it moves with the saccade, so that in fact the saccade and the eye are not flowing over the cube, that the cube simply gradually dissipates and disappears as an image. So what that's telling us, and what this is telling us, is that flow, motion, is at the very heart of the specification of form and dynamic form. Now, the problem that arises with flow fields as the function of form is that, or the function behind form, is that the specification of form is thus very dicey or uncertain. That is, there's inherent uncertainties involved in computing the velocities of these flow fields. This is because the eyes are apertures with a limited field. So this is termed the aperture problem. Here in the picture we have a grating that's moving to the right, and as it passes underneath the aperture there, which is exactly what an eye is, our eye does not have an infinite field, it has an aperture on the world. As it passes under that aperture, we notice that we move from the horizontal motion that the grating has to, because the line ends are obscured, a downward motion that is perceived. So we're not getting the horizontal component of the motion. What the velocity is being computed from partial information on its downward motion. And therefore you end up with a probabilistic computation of velocity. Take another example. We have an ellipse rotating, a normally rigid ellipse. But if you look at its edges, the edges or the periphery, the perimeter, it actually is composed of a series of velocity vectors. It can be conceived as a set of velocity vectors, as you can see there in the picture. Now, we come then to the probabilistic constraint. This was a constraint proposed by Weiss, Siemens, Schelling, Adelson in Nature Neuroscience, 2003. And the constraint is motion is slow and smooth. So this constraint sounds strange, but it can be incorporated in mathematically into a network such that where the network is responding to the velocity vectors, and this constraint is built in. And if the constraint is violated, if the motion is too fast, what happens is that rigid ellipse becomes a wobbly, non-rigid, floppy ellipse. So even the rigidity of this rigid ellipse starts to collapse under the violation of this probabilistic constraint, namely motion is slow and smooth. So too great a speed, we violate the probabilistic constraint used by the brain in processing these flows. So this is termed Musati's illusion. This gets worse. Again, following the notion of form is actually a function of velocity fields. Here, I'm picturing a cube that's made of wire edges, and it's rotating. Now, when a cube rotates, it has a symmetry period, and that symmetry period is equal to 4. That is, the cube is carried into itself, mapped fully onto itself every 90-degree turn. So with every 90-degree turn, you can't tell the difference from where we started, assuming that there's no markings on the cube faces. The cube looks just like it did before the previous 90-degree turn. So it's constantly rotating or carrying into itself every 90-degree turn. It does that 4 times, or has a symmetry period of 4 for each total rotation. Now, suppose we strobe this rotating wire edge cube. Now with a strobe light, okay? What we find is if we strobe at an integral multiple for each revolution. So if I strobe the cube 4 times per revolution, or 8 times per revolution, or 12 times per revolution, 8 being a multiple of 4, 12 being a multiple of 4, 2 times 4, 3 times 4, 1 times 4, what we see is indeed a rigid cube in rotation. However, if we strobe the cube, our rotating cube, at a non-integral multiple, 5 times per rotation, 9 times per rotation, 13 times per rotation. In other words, 4 divided into any of those numbers does not come out evenly. So a non-integral multiple, or it can be termed arrhythmic, out of phase with the symmetry period, what we see is a non-rigid, plastic-like, wobbly, not cube. So again, like in Musati's illusion with the rotating ellipse, the very rigidity of the cube is gone. Our perception system is using these velocity fields, and with the increased velocity, or in this case, the out-of-phase strobing, we're violating constraints that gradually cause the loss of the specification of rigidity. There's various ways to conceive of these constraints. One could simply be that temporal symmetry is always equal to spatial symmetry, and we're violating that. That is, a cube in rotating should emit very periodic, natural periodic pulses, shall we say, if you rotate, but in phase with, the actual structure of the cube. It's a regular cube, but when that's not present, that is, we're losing our temporal symmetry because of the strobe, the non-integral multiple strobe, we start to lose the rigidity. So the conclusion based on these flow fields as an underlying element of form is that form is always probabilistic. It's always an optimal specification based upon the best available information. This is Weiss, Simoncelli, and Adelson's conclusion. This is due, of course, to the inherent uncertainty of information in these velocity flows, which make the computation of velocities uncertain. There's a deeper and more profound reason due to the nature of time itself that we'll ultimately explore why this uncertainty is intrinsic and cannot be avoided. If we take this to our holographic model, where the brain is a reconstructive wave passing through the holographic field, well, we would be saying that the specification of the external field is always an optimal specification. That is, it's a probabilistic specification based on the inherent uncertainties in these flows and therefore on the best information available. Now, I'm stressing this because this idea that we're seeing what is out there exactly is true to a certain point depending on the information and how it's being processed in the holographic field. Take, for example, this particular example where I've recorded on my hologram plate information for two different objects. For frequency 1, as the reference wave, I've recorded the cube as the object. With frequency 2, as the reference wave, I've recorded a cup as the object. Both of these wave interference patterns are recorded on that holographic plate. So what then is a valid decoding of the information on the holographic plate? If I send the reconstructive wave F1 through, I see the cube. If I send the reconstructive wave F2 through, the cup is specified. But this is from an omniscient observer. Okay, if I send a composite frequency through that's containing frequency 1 and frequency 2, I would see a fuzzed image, a composite image of the cup and cube. That's what would be specified based on the information in the field. It's difficult to say that that's actually wrong, that that's invalid or non-veridical, because the information for both the cup and the cube is there. Just as the information for the rotating cube is there, but if screwed up with a out-of-phase strobe, I'm seeing a wobbly, non-rigid cube, plastic-like, and therefore we would say, well, is that an illusion or is it reality? Well, it's the best information available in the holographic field. So, as I'm saying here, the fuzzed cup cube, is it an illusion? No, not really. This is just an optimal specification based on information in the hologram given the reconstructive wave I used. Is the wobbly knot cube an illusion? Or is the non-rigid ellipse an illusion? Well, for indirect realism, which holds that all images of the world, our vision of the external world is in the head, these illusions are the very best evidence to them that the image has got to be generated by and is in the brain, that we're not actually seeing objects where they are in the external field. But from this perspective, these illusions, whether it be my cube cup, whether it be the wobbly cube, whether it be the non-rigid ellipse, are simply optimal specifications of sources within the holographic field. And they're just as external to us as anything else, as the coffee cup out there on the table. So this is a quite different view of illusions. So what have we seen thus far? From Bergson, the brain is a modulated reconstructive wave, and this wave is specific to sources within the external holographic field. From Gibson, the modulation patterns are driven by the invariance laws structuring these external events, whether it be the velocity vectors, texture gradients, tau ratios, and more to come that are all defining these events, whether it be of flowing fields, cups moving back and forth, etc. For both Bergson and Gibson, the image is not in the brain. The brain, as a reconstructive wave, is simply specific to the external environment. There's something unsaid here also, I've been implying it, and that is that Gibson's model requires Bergson's holographic framework to be understood. For Gibson, the brain is resonating with information. It's resonating with information specifying the environment. The brain is therefore specific to the environment. But the processes underlying the resonating brain look nothing like the coffee cup either. Gibson never explained how the image of the environment actually comes about. He is effectively assuming Bergson's holographic field and the brain as a reconstructive wave as a mechanism for image specification. To explore now a bit. For Gibson, an invariant defined over time, say over a velocity flow, cannot be transmitted as a bit along the nerves. Let's stop there for a second. What's an invariant defined over time? Notice that these edges of our cube are defined over these velocity flows as the flows move towards us in a way. There's always this juncture between the two flows, a discontinuity between the flows. That's a form of invariance. The point from which the optical flow field coming from the mountains with the sun up there expands, the point of optical expansion is a invariant point of the expansion of these flow fields that's defined over the movement, over time, over the movement of the flow. But are these things bits, such to speak? Are they static? Is this a static piece of information that you can transmit along the nerves? Well, for Gibson, these things are not such that they're static pieces of information. An invariant is not an invariant defined over time, such as our cube edges, does not exist as a static piece of information. It does not exist in a static instant of time. We can't find it at a static instant, at a precise point in time. An edge or a vertex of a rotating Gibsonian cube, therefore, cannot be stored in a static memory as a value or a static feature. Now, for Bergson, there are no such things as instants. in the first place. There's nothing static, there is only flow. So we'll be exploring this as we go. For both, current physics conceptions of space and time are not adequate for psychology, for a theory of mind. So that is, cognition, memory, perception require a different model of time. This was the opinion of both Bergson and Gibson. And that is, again, the standard model of time and space, what's better termed the metaphysic of space and time, needs to be revised. So what I'm going to launch into here with these velocity flows and jumping off these velocity flows, and therefore the nature of the events that we're perceiving and therefore having to store, is an initial discussion of some of the problems of actually perceiving these events from a memory model point of view. Now, first of all, we noted in part one that Bergson's model of the brain, and Gibson's for that matter, requires a very real concrete dynamics. As concrete as my AC motor over here in the right generating a field of force. You need very concrete dynamics to generate that field of force. You're not going to do it with rubber bands and toothpicks and a box. You need magnets, wires, etc. Secondly, this device is operating in a very concrete time or concrete flow of time. Now, we'll see what this means, but in contradistinction, a computer's operations are carried out in an abstract time, in an abstract space. There's no particular concrete dynamics that is required to support the abstract operations as well. Remember, an abacus, a Turing machine with a reed head and infinite tape, beans and shoeboxes all suffice. So there's no particular concrete dynamics in the computer model as long as I can carry out the computations. If I can get A plus B plus equals C, A plus B equals C, out of any of these devices, whether it be abacus, Turing machine, beans and shoeboxes, I'm fine. That's all that's required. And you can already kind of intuitively see that the time that I'm doing this isn't particularly irrelevant either. Now, these operations really carry out syntax rules, which can be defined simply as rules for the concatenation and juxtaposition of objects. So I can be concatenating two cubes together, juxtaposing them. It's a very spatial operation, purely spatial manipulation that syntax rules are dealing with. And by objects, it can't necessarily just mean cubes. It can be marks on a page. It can be A's, B's, C's, D's, the objects of the alphabet. It can be, or the numbers of a number system, etc. They're abstract objects, and the syntax rules define their rules for concatenation and juxtaposition. It's a high-level view of syntax. So in algebra, we have A equal B, C, or B equals A over C, etc. In linguistics, or grammar, we have a rule that says a sentence can be rewritten as a noun phrase plus a verb phrase. Other rules that say a verb phrase can be rewritten as a determiner plus a verb, or determiner plus a noun phrase, etc. These rules however, are unaffected by the actual nature or flow of time. They can occur instant to instant or square to square as on a Turing machine tape. As the tape runs under the read head in a Turing machine, with an instruction on each square, so to speak, the Turing machine executes, square by square, instant by instant. Or I can move the abacus beads at my leisure. Whether the time to move my abacus beads or move my Turing machine tape is extremely fast, lightning speed, or geologic, moving at the rate of glaciers, the same computational result is achieved. So the operations are effectively scaleless. They have no scale of time. They function and are unaffected by scales of time. The problem we're going to see, however, is that there are many possible scales of time. I've got a buzzing fly of our normal scale. Our normal scale is filled with buzzing flies flying by. But that's not the only possible scale. There's a scale where the fly is flapping his wings slowly like a heron. There could be another scale where the fly, is stock still, motionless before us. There are multiple scales, and what that says is that the brain processing as a very concrete device in concrete time is very intricately involved in specifying a scale on the time flow of the holographic field. And so we start to wonder how scaleless operations have any relationship whatsoever to what the brain is actually doing. As I said, these operations proceed instant to instant, to abstract instant, I should say. These are very abstract. It's an abstract time. The operations do not require that the instants be in any way connected, for that matter, or continuous, that is melding into one another, organically glued together. The abstract operations are required in only these. So as long as I carry my operations out, whether it's move the abacus beads slowly, instant by instant, or day by day, I can move an abacus bead one day, come back and move another one the next day, or move the Turing machine tape one square the next day, one the next day. I'm going to get the same computational result. But there seems to be little relation to the actual world of scaled time that we see, namely buzzing flies versus heron-like flies versus motionless flies. Again, note the buzzing fly is a specification of the past, and the fly's wing beats have long ago come and gone. I mean, when we're perceiving that fly with hundreds of wing beats, we're seeing something that long ago happened in the past. So how is this past specification possible? We're going to be exploring that. And the buzzing fly, the moving fly, or the rotating cube are, along with this, time-extended events. Not only are they in the past, but they're also time-extended in the past. They're dynamically changing forms. And we're perceiving a past continuous motion. We're seeing flies buzzing by. We're not seeing motionless fly after motionless fly after motionless fly. We're not seeing static instants. We're seeing flies buzzing by. We're seeing cubes rotating. We're seeing leaves twisting slowly and falling in the wind. We're seeing these time-extended motions. So we have to explain the glue that would glue all these abstract instants of the computer model together for us in the first place. Now, one question then is, well, what is the memory? One way to put this is, what is the memory that supports dynamically changing forms? Whether it be my cube over there, whether it be the fly who's dynamically changing as he buzzes his wings along, etc. Even the leaf dynamically changing as it twists and rotates and falls down to the earth. So we're into a memory problem that's also a nature of time problem. Again, there's no actual continuity in the computer's operations, in state to state, instant to instant. And cognitive science, however, views the brain in exactly the same way. Both AI, artificial intelligence, the computer model, and cognitive science and physics share an underlying metaphysics on space and time, where we have basically a set of instants, instant to instant. So the question, again, how do we explain the continuity, the time extension of perceived motion? What is the glue of the instants? How do we get the actual rotating cube? How do we perceive the cube in rotation, or the fly buzzing by? Is there a form of memory underlying perceived events? Another way to put this, how does memory support a dynamic form? Remember, we're talking forms like the cube defined over flow fields, overflowing fields. Now, for current science, the question of memory is always a question of storage. So we would be asking, how does the brain store the velocity flows defining a rotating cube, or any event, be it the buzzing fly going by, the twisting leaf, etc.? One answer is by storing samples in the brain. The other is we parse the event. We parse the dynamically changing, flowing event, whether it be rotating cube, falling leaf, or in this case, as the picture shows, biting a carrot. Okay, I would parse it into states. So Barceló, a memory theorist, proposed this. How would I store a biting transformation? Well, as 3 states, he argued. Mouth closed, mouth open, mouth closed on the carrot. Those are my 3 states above. Again, we should note, biting, in this case, is actually a facial flow field. The face is flowing as the mouth opens and closes and opens again. And it's as difficult to store as the flow fields across the sides, the velocity flows of a rotating cube. The difficulty here is each state or sample of my biting face is a static point, or static picture, shall we say. It's like I've laid 3 snapshots out in a row, sitting on a desktop, 3 snapshots of the biting, or 3 snapshots of the rotation. The desktop here is equivalent to a form of short-term memory store, where I'm perceiving the biting and I'm storing each state in a short-term memory store. Each of the 3 states above is being stored in a short-term memory store, because I'm trying to explain how I perceive this motion. And so they're stored in the short-term memory store as though they're sitting on a desktop. But now the question becomes, how is the motion reconstructed then? Am I using some form of scanner? Given I've got the 3 states stored there, does some internal scanner get activated who scans the snapshots to turn them into a motion? An actual opening, closing of the mouth, moving into the carrot, etc. Well, who scans the static snapshots? And that is our internal scanner. Well, then, let me put it this way. What we have is an infinite regress, because now we have to explain how that internal scanner registers motion. We get another scanner behind him and yet another scanner behind him. And in other words, we have an infinite regress, and we cannot explain how we reconstruct motion via an internal scanner. We just got an infinite regress problem. Another difficulty is that a sample is equivalent to a strobe in our cube case. But what we saw in the rotating cube case is a single strobe, that is a sample, is not sufficient to specify form. If you think about it, the strobe was actually sampling, sample by sample, the rotation of the wire cube, state by state. But if you kept it in phase at an integral multiple, you saw a cube. But if you sampled out of phase, you were getting a wobbly plastic-like object. So just one sample per se is not sufficient, or any kind of sampling per se is not sufficient to specify form. So I can't lay out 3 snapshots of the rotation of the cube and expect that that's sufficient to specify the form of the cube. Now, what we have, however, in trying to account for the registration of motion, namely events, via some static memory store, is that we've got an approach that's almost ubiquitous, absolutely, in the literature. And of course, they're proposing that we store these states in a memory store, and then there is some form of vague integration of the samples, where integration is what? Again, a sampling, a scanner. That is, integration is actually an implicit appeal to some form of scanner, or somehow melding them together to form a continuous event. Just believe me when I say, in the literature, this is very vague at this point as to how an event is stored as samples of the event, instance of the event, and then somehow registered afterwards via the short-term memory sample storage, stored as an actual dynamically changing, moving event. Let's take an additional example. And in this case, I'm talking about a neural network or connectionist approach to recognizing form. And the authors, Hummel and Biederman here, I'm going to mention here at already at the bottom of my bullet points. Hummel and Biederman, 1992, had noted that, well, if I take a cube and cone in the picture up there, and I break that form pair down into features, my vertex, my curved T vertex, these various vertices, and of course, they're not including the edges and lines, but in our picture there, I can store all those in memory. Okay, but how do I get them back together? They noted, because I can take my jumbled set of features that I've stored, and I can put them back together in all kinds of different ways, not necessarily looking like the cube and cone at all. An interesting question. I'll go to their solution in a bit, but it's only a quote-unquote solution. But the first problem with features in the first place is what's called the correspondence problem. And as the cube or cone rotates, or my tree grows, to compute form, you've got to track the features from frame to frame, or snapshot to snapshot. So as the tree grows, we have to fix on various features various of the branches, for example, and track them as we go across my snapshots. These could have been simply, and I don't have a nice picture of it, but it could have been the rotations of a cube, and therefore we have to track from frame to frame the vertices and edges of the cube and keep them identified from frame to frame. The difficulty, and I'm not going into great detail here, but this problem was universally determined to be intractable. Impossible to keep track of these features if we break the object down into features from frame to frame. In fact, this was the foundation of the move we've already seen to relying on velocity flow fields. The field said, heck with, the academic field said, well, the heck with this feature tracking problem or the correspondence problem, let's just rely on flow fields in the first place. Hence, the Weiss, Simoncelli, and Adelson approach that we looked at with velocity flows. Now we know that there's no photograph of the cube or the coffee cup found in the brain. There's nothing like that. So because there is no such coffee cup, for example, nice image of the coffee cup in the brain, and nowhere in the brain in its neural structure have we found such a thing. The academic field has been led to a discussion of disassembling the event into these features and storing these in separate areas in short-term memory. And this is why this approach is being forced in the first place. We have to deal with the fact that we don't find this image in the brain. So maybe what's just stored in the brain is all these little features. Hard to find in the brain, but maybe they're there. Okay, and the features, of course, now must be reassembled as the event. I've got to bring all those features back into the cube and cone, or even worse, the rotating cube and cone. And as I said, right here, if the cube and cone were rotating, I'd have to disassemble the cube and cone into features and reassemble them again in real time, over and over again, and not to forget, somehow maintaining continuity, because I've got static samples. If you can imagine what's really being proposed, I take an instant of time, I break down the cube and cone into a set of features like that, then store them away. Meantime, it rotates a little more, and I got to take another snapshot, break it down into features, and store it away in my short-term memory. And it's rotated a little bit more. I've got to break it down into features, store them away, and now I've got to put them all back together, and somehow I've got to invoke my scanner or something like that to actually create the actual rotation of the cube and cone as it rotates around. Again, I've got to solve the continuity problem, and this is usually by some vague appeal to integration, quote unquote, which is vague to say the least. And of course, there's this underlying question is, well, how do you put the features back together that Hummel and Biedermann noted in the first place? Hummel and Biedermann had proposed that the forms are decomposed into Gions. Now, Gions are what they considered basic three-dimensional structures like bricks and cones and wedges, and the event is composed from these. So in this case, I would be storing in my cube and cone picture up there, I would break that down into a brick and into a cone, and I'd have some sort of relationship specified as the brick goes on top of the cone. And the brick is also got to be transformed a bit to be more of a cubical brick. Okay, the Gions, in other words, were like the picture on the top of the puzzle box we get when we get a puzzle, and we have a nice picture there, and that tells us how to put all the pieces back together. I'm just having fun with this because you can see the dilemma that memory theory is in as far as any kind of decent theory of the perception of time-flowing, time-extended events, like rotating cubes or falling leaves. In this particular case with the Gions, there's so many problems, I'm not even going to go into them, but simply to take a salient one we've been working on. For one thing, as we considered the Gibsonian cube and its rotation, the features in the cube were simply sharp discontinuities at the junctures of flows. This is to say, the features do not exist without the flows. They are invariants over flows. In other words, the static storable features that Hummel and Biedermann were considering do not exist. This is to say, the storage problem is way worse than they think. They have to be storing flows. This is all just another form of sampling. Again, we're taking snapshots, static of the event, breaking them down, disassembling them into features, whether it be Gions, whether it be, or just features. And the problem here is it's equivalent to the network taking samples of the rotating cube. But we know that that can't work. You know, the non-rigid wobbly cube shows that just taking samples does not work. You'd have to have a sampler that's completely in phase with the symmetry period. In other words, the sampler would have to know that it's going to rotate, it needs to sample at 4 times per revolution or 8 times per revolution. It would need precognition. And then you would what if you had 2 or 3 cubes rotating at different rates? How does the sampler sample in phase with the symmetry period of the cubes rotating at 3 different rates? Not possible. But yet, implicitly, a network like Hummel and Biedermann proposed, whether using features or Gions, is inherently sampling and inherently hits this problem. It's just, they're not responding to the realities of velocity flows. Bottom line, there's no discussion of how the brain stores velocity flows, nor any engagement with these problems. So if we consider all that we've been going through, the problem of storage of samples of the event, the problem of trying to store features, reassembling them, disassembling them, etc., and the absolute vagary thereof, in other words, the entire vague solution to registering continuous event flows, leaves falling, cubes rotating, we hit the wisdom of Gibson's statement. For where is the borderline, he asked, between perceiving and remembering? Where do percepts stop and begin to be memories? Or in another way of putting it, go into storage? The facts of memory are supposed to be well understood, but these questions cannot be answered. So we move on to where we'll go in part 3. I said before, the specified image is an image of the past. This is where the optical problem of image creation becomes also a problem in physics model of time. When we see the fly buzzing by, his wings beating 200 times per second, we're seeing a blurred summation of an already past history of the fly's motion. And if we imagine this particular motion, 1 second of the fly and his wing beats spread out in time, it would be a vastly long event. And you could imagine watching each wing beat move, where the wing moves up 1 degree, then 2 degrees, then 3 degrees, then back down again, etc., and spread out over this long, long history. But this entire event is being collapsed at a scale of time for us as buzzing flies. But we're seeing the fly as a past transformation of a small portion of the external holographic field, and we've got to understand how that's possible, and this is why we're going to bring in Bergson's model of time to solve some of these difficulties. Again, as I noted, we got to remove the homunculus, the looking concept of a little man that sits behind the brain and views a projected image. And as I noted before, the image is not really projected by the brain. The brain is simply specific to a source. But this is going to move us into the problem of time, and we're going to, in the next session, look at this statement of Bergson's. Again, questions relating to subject and object to the distinction and the union must be put in terms of time rather than of space. So next time, we'll be dealing with the classic, what I term spatial metaphysic. We'll be looking at Bergson's temporal metaphysic. We'll be looking at scales of time and the origins of scales of time. We'll actually be addressing this question, how we see the past and how we see time extended motions, and ultimately addressing the homunculus and the profound question of the relation of subject and object. Down the road, we've still got the question of what is thought and cognition, the implications for AI and the notion of the singularity, where robots equal then and then exceed human intelligence, and what that would mean to achieve in reality, given Bergson's holographic wave reconstruction model of the brain. Why do AIs need and will never have explicit memory, free will and voluntary action, implications for education, discussion on evolution, mind, and consciousness, and then very relevant Bergson versus Einstein on relativity, because our model of time is all important here. So on subject and object and time next. Till then, signing off.